трансляцию включил до панели. Там, если можно, кто-нибудь из вас тогда после трансляции перекиньте наши файлы вот, в чат. Сложно через телеграм.
Как это сделать, вы знаете?
Нет, ну как бы наши, так сказать, коллеги, они через QR-код на телеграм заходили, ну и вообще через интернет. Можно по почте себе переслать, но просто не все любят, даже вводить. Просто понятно, что это больше вам надо, чем мне, поэтому, ну, как бы я в какой-то момент сделаю, но...
Проблема в том, что это основно людям, которые не ходят. Проблема в том, что это основно людям, которые
Ну да, есть такой нюанс, конечно, потому что все равно вы, как говоришь, конспект пишете, поэтому... Не, ну, конечно, писать конспект полезно. Это, ну, можно дописывать, что не понимаешь. The formula for ramification. So, yeah, mainly preserved under in our studies. So just here you have the ring A, and B is so number will be N now. So we have also A, which is so if you take it's K, and B is so A is supposed to be also we assume that A is integrally closed to guarantee that trace belongs to trace of elements of B, which is integer elements, belongs to A. And B is integral closure A in L. Yeah. So, so here we are now, we can study, so if so on previous lecture, meaning that so that A is integrally closed equal to 1. So we have derived on previous lecture that B is also is diagonal. So integral, I mean B in this integer morphism, meaning that all elements of B are integer over A. So of course this doesn't guarantee that your ring is dedicant. For example, so we can also give, you can take A1 and you can take just vertical projection. So you take vertical projection, then it will be dead. So this here we apply that.
And there will not be any problem.
Results tangent point. Yeah. But this is a usual situation, and you should understand that. So what we shall discuss today is specifically how to measure this. There are some. So this is somehow the measure of tangency. Yeah? So, for example, also you can take semi-cubic curve here, and we can project like this. Yes, so I mean cubed. Yes, so when you draw the tangency, it will be tangent. Yeah? And tangent, more tangent, any morphism. Yes, so between. I mean, if you think of this locally or more generally between the curves, so if you think of the finite morphism, you put. You may think of it as some kind of projection, and this is somehow illustrated. So, B is dedicant, and this inclusion of A into B induces the morphism or in opposite wave spectrums. So here very was A, so which will be prime ideal, and not equal to 0, as we also have proved. We are starting with a given ideal P, and as I discussed, we are interested in the equation for preimage. Yeah, so we can take preimage. I do not want, this is inclusion, yes, so this can be thought as, I do not give any meaning to this, just not to denote it like a pullback. To write down the preimage on this point P. And this will be some set, so we shall discuss the structure of the set. And as we have discussed it, in geometric terms, this will be the following. So we start with P inside a prime ideal. Could you have a look? So if we're online. Yeah. So if you have a prime ideal or any ideal, you may form the following. So you can consider it as a subset in A, and A is we have an inclusion in, so we can consider P of B. And now we have Dedekind ring, so we can decompose it in prime ideals. And notice, of course, that this. If you look at this prime ideals, they are precise that everything sits inside the beta I, so this implies that beta I, since it contains p beta and just beta I intersection with A, we know that it is prime, so it is maximum. And of course, p beta contains automatically. So this what? So we do not even need to know that it is prime. It is just is contained here, and the p beta intersection with A it clearly contains p. Yeah? And this implies that beta IA is a larger ideal than P a priori, so this implies that since P is maximum, then these ideals that appear in this decomposition clearly are ideals like what? So beta I all lie over So also, the thing is that we can introduce some characteristics. Numerical characteristics that allow us to give control on these EIs. So let us do it. So notice that. Additionally, let us introduce Fi, the inertia indices. So it is not clear why we call it like this. Yeah, so EI are called ramification indices. So EI are called ramification indices. And Fi are called inertia indices. So, and they are defined by just thinking of the following. So you take beta I modulo beta I, and you look over the beta I are maximal ideals. So this is a field, and this field actually contains P simply, this field contains A mod P simply because you take B, you take the quotient of beta modulo beta I, and when you restrict it to A, so this is again just taking A intersection with kernel of pi restriction to A, so which is just kernel of pi restriction to A is intersection of kernel beta I with A, and this is precisely P. And so this is just A mod P. So A maps to this thing that sits inside this quotient, and it allows us to see, so that this is a field that contains this field. But notice that our assumption, so we have proved that B is finitely generated modulo over A. That wasn't clear, so that B is finitely.
But may I ask a question?
Yeah, just let me write and then you can finitely generated module over A. So this of course implies that B mod beta I is still finitely generated with the same generators. So you can speak about this now. Yes, so which is so this means that this is finitely dimensional vector space over A mod E, and this number is fine. Yeah.
Yeah, I want to ask, so we know, we said that beta I lies in preimage of P.
Yeah. Meaning that you formally apply beta, the formula for projection, and this is just taking extension in the sense of commutative algebra, or here, not extension, contraction. This is called contraction, meaning that you take so you have a morphism between rings, homomorphism between rings, and you take preimage and the homomorphism of this idea.
Yeah, so yeah, and do we know that this beta i's, it's everything that lies in preimage?
Yes, this is precisely everything that lies in the preimage, because you have the following. Yeah, so that is a good question. But notice, yes, of course, defining this, we could think that EIs are zero. Yeah, so at least we should know that EIs are non-trivial. But notice that so again, so this was good question. I think on previous classes I didn't even discuss it, but yeah, so you take beta, so this is so line over P. So this of course means that beta intersection with A is equal to P, but this means that beta itself, it contains ideal P beta. But we have discussed that, that it can ring, yes, so divisibility property. That this implies that P beta, so P beta is divisible by B. And this implies that the P are not trivial in position. So
that's true.
Yeah, by property of Dedekind rings. So the divisibility property. Yeah, so of course this there are some moments about associated prime decomposition. And here the situation can be a little bit more subtle because you have the following. So decomposition is not related directly with pre-images here because you have objects of different dimensions. And it can happen that you something map in the lower dimension, but you have higher dimensional fibers. And of course, so you should think about components that correspond to, so that maps suggest, first of all, they should map subjectively to this, and in associated prime decomposition, they should be essential. I mean, there could be, of course, points, or in the component of higher dimension, there could be a point that is not dominating P, so that means it maps entirely. So this means that this beta would contain P beta, but intersection can be a larger ideal than we expect. So this is precisely the dimension of the base. And also you can have, I mean, if you allow not finite morphism but more general, then there could be a components, of course, of higher dimension that are dominating. I mean, there could be just, sorry. Yeah, so they are dominating. Yeah, so they can map non-trivially. I mean, even finitely, but what I wanted to say about these components, they could be a subset in this set. Yes, so I mean, this will look like that. For example, like E2 maps to A1. And then the problem is that even if they appear, they do not appear in the canonical part of associated prime decomposition. The problem is that a general statement of Dedekind properties, this decomposition is somewhat the following. So you take ideal and you decompose it into intersection of primary ideals that are associated to some components which are prime. And here you have components of, so they are associated of the ring modular Qi. Yes, so, so these components are prime, and but some of them are canonically defined and some of them not. So if they are minimal, meaning that they just this ideal is not contained in other associated component. Yeah? So this means that they correspond to components of maximal dimension. And the lemma that one proves just by localization, and these components are defined uniquely. And these are precisely the components that we see in this decomposition for Dedekind ring. So we know that in this decomposition, these components, they just should appear simply because they correspond to the components that are defined canonically. But the choice of this additional component is not unique, and that's why one cannot guarantee that you can use it in your decomposition. So there are two moments, geometric one and non-geometric one, but in the case of the Dedekind ring, they are both coincident. Yeah. So this, but this, I mean, for those, that was for those who has heard of associated prime decomposition, of course, we do not need it technically in our proof. Yeah, so here notice that you have this some kind of examples when this happens. I mean, when this non-trivial indices happens. So let me maybe say something about this. So this is even visible in a very easy situation when you have R and you consider the quadratic extension of so you consider the morphism over R, so of A1 into A1, so which is just Z square, yeah. So if you can, so this means that this is a morphism of R of yeah. So meaning that we have discussed that this means the following. So this means that you have the in the map. So if this is F, so you have homomorphism on the functions that is a pullback map, and it maps RT into RZ by mapping T precisely to the value of the coordinate, so T maps to Z square. And we have discussed what are possible ideals, so you have picked 0, and here you had precisely ramification, yeah, because we have found out that if you take ideal denoted by T, it maps to, so here ideal T is equal to 0, yeah, and here it is ideal Z square, yeah. So this is precisely the square of the ideal, yeah. So if you have an ideal here which corresponds to the point T minus A, where A is positive, yeah, then it has precisely two preimages, yeah. So this decomposes into ideal T minus square root of A and T plus square root of A. And if you have T minus B where B is negative, then it doesn't decompose, and you calculate, so you can calculate the following value. Yes, so you can calculate R modular. So this means that the ideal that you are obtaining, so this ideal will be T minus, so Z square minus A, yeah? So this Z square minus B, it will be a prime ideal, yeah? So, so this means that T minus Z minus B, Z square minus B is prime ideal, and R of, so you are calculating R of X, so R of Z modular Z square minus B, yeah, and over R, yes, so over, so you consider it as a field over R of T modular T minus B, which is of course R. And since clearly this is quadratic extension, so this is, so you are adjoint the imaginary unit, so this is isomorphic to C. So you see that C is quadratic extension of R precisely, that from the viewpoint of the points of spectrum, this is not decomposable. If you allow that, if you take C over Z, yeah, so if you extend the scalars, so this ideal, to this ideal you apply the operation. So notice that in this case, in the geometric case of curve, so we can extend,
So looking from inertia index, this is like there we have inertia index 2.
Yeah, so here you have inertia index 2 in this ideal, and in this ideal you do not have an. Oh, sorry. Yeah. So yeah. So here you have ramification index 2, and here you have inertia index 2.
Yeah, and here in Z square you also have inertia index 2.
Here you have inertia index 2, and here you have inertia index 1. But
so, why is it so?
because the ideal is just R of t modulo z. I mean, maximal ideal is z.
Yeah. Oh, yeah, that's
Yeah,
true.
so,
yeah, of course.
so here you have so it is a good question that you asked. So f is equal to 1, yeah, and e is equal to 2 here, and here you have f is equal to 2, and e is equal to 1. Yeah. Just because the ideal appear, so this is a prime ideal, and it appears as the power, with the power 1. And these ideals are just, so this means that you have this decomposition, t minus a, when you, so z square minus a. So the ideal becomes z square minus a times r of z. So this is an element, so r of z. So this is precisely written as z plus square root of a times product of two principal ideals. Yeah? So this ideal z square r of z, it is just a square of ideal z, and so here if you take r of z and you take z square minus b, this is just prime ideal. So this is just z square minus b. Yeah, so I mean on the left side I'm writing explicitly what we have to do to take an generating element and extend the ring. So here you have to write t minus a. So this is like t minus a in last coordinates. So this is t, and this is t minus b. You are rewriting it by substituting z square, generate the ideal, and you get the following relations. So if you calculate, so here you have this ramification, and this is here you have this one. Yeah. So so we can the remark that we can of course extend fields, extend base field. Yeah, but this kind of extension, it is not so. I mean, if you take so everything, for example, we defined over k, so we can take k tilde. Yeah. So I mean that the algebra A itself can be finitely generated over k, and if you take fraction field, it will be also the field over k, but it will be related in a different way. So then you can do the following. So then you can consider, instead of b, you can consider the tensor product with this larger field k over k. And if you have ideal that sits in b, then you get the new ideal I tensor k over k bar, but not and notice that even if this ideal is prime, so when I is prime, it is possible that ideal after you extend it, this way won't be prime anymore. So not prime anymore. And I mean, after such extensions, even B can be, so the variety which was irreducible from the viewpoint of this field K can become reducible over K, but let us avoid this situation. But anyway, even for points, you see that, so precisely in this picture, that you started with ideal over your ring, but after multiplying it, you get that it is not prime. And the reason here is, I mean, is the following, that, so what was written here, it is B modular I. And if you take tensor product, it is equivalent to, so the tensor product is, so has the property that this is isomorphic to, so this commutes, taking quotients commutes with taking tensor products. And this means that, this means that when you do this, yes, so what we shall see? We shall see that we have to take, so in our example, you will see that you take C and you pass to C times C over, if you extend the R to C, yes, so you pass C to C over R, and this is, I mean, it has dimension 2, yeah, so it is C plus C. So. And so this is, you see that this quotient is, will have now 0 divisors, so precisely this corresponds to this kind of taking decomposition. So taking decomposition into different points into reducible. So, yeah, so this one should understand. So, but when you are working in number theoretical case, of course, there is no option to extend the field, base field, yeah, because you do not have any inclusion of the quotient field in your ring. Yes, so that's why we are thinking, I mean, we're keeping in our mind that this is thick point, but we do not have a way to decompose it. Yeah. But geometrically, well, this means that we have to work with it as if you have a geometric intuition, this should be like a thick point, like the union of several points. But in our case, this is not so clear what it should mean. This is a kind of new effect for us. So the formula that we want to prove is that, so proposition, this is very important technical formula that says something about this ramification indices, that n is precisely the degree of the extension. Is precisely so the sum of E beta lying over P and here I would suggest the notation that I mean so since beta is precisely so runs over the set of I mean, in the literature, people sometimes like indices, yeah, so like to write indices for the sets, I mean, for finite sets, yes, so for ideals lying over P. So, but here I would like to write down like E beta, F beta. So here the summation is taken from the element of the set of ideals lying over P. So from my personal taste, there is no reason to write down that the set contains B1, etc., Bn, and here you put indices Bs. So this, yeah, so this number is equal to 10, yeah? That we have introduced. So notice that, yeah, so this here remark about ramification indices. Yeah, so and that we shall use also. Yeah, so notice that this ramification. So when you are considering such such decomposition, B1, E1, etc., B K. Okay, so we can pass to localization. So pass to localization with respect to BI. Yeah, so meaning that multiplicative set is just beta minus BI. Yeah? So, and this will give you the decomposition that, yeah, so all ideals will become, so since you have the property that beta I do not contain in beta j, is yeah, so here do not contain beta j. Yeah, so this will imply that beta j intersects non-trivially with this multiplicative set. Yeah? And this will mean that beta j will contain unit after localization. After localization. So this will imply that the ideals become the whole ring. So what you will have is that P beta in beta I after localizing is just a beta I in the corresponding degree. Yeah? So you reduce this kind of picture to the case of one ideal, and so this is precisely what we say about the local check. So from the viewpoint of the curve, you have yeah. Also, let me say that when the if you take if A is Dedekind, so we have understood that A beta is Dedekind. So this implies. Ой, я что-то тут. Yeah, so this implies that, and we have discussed that it has only non-trivial prime ideal. So we have proved that it is any ideal. So it is principal ideal domain. So any ideal is principal here. So in particular, beta I is just some pi, where it is called uniformizer, униформизующая, я поэтому букву У. So this is called uniformizer, and this is some kind of local coordinate. Yes, so from geometric point of view, if you look at this situation, you may think that yes, so that your map here will be precisely the coverings in the sense of complex spaces. Yeah, and here you can think of local coordinates, and this is precisely uniformizer is precisely corresponds to the choice of some local coordinate. And so the claim is that any function can be just you have this kind, so can be written as the product of uniformizer and some power and invertible element in this point, in the neighborhood of this point. So this is just the remark, and let me discuss the proof of proposition. So I mean the following. So this kind of equality, it is local equality. Yeah? So this means that it can be checked locally. Yeah? So meaning that if you have a function and you want to understand that it belongs to precisely it is written as or belong to this product of ideals in some power, you can look at each point separately and in the neighborhood of the point. So that's why I mean formally it is not so visible when you're reading the text, but the geometric intuition should be like this. So proof of position. Yeah, so the proof is quite subtle here because it uses, I mean, it is on one hand straightforward, but it is not so clear. I mean, there are moments that are quite important. So specifically how to relate this degree. Yeah, so L over K is equal to N. Yeah, so you have to relate it somehow with the number that is written above. But then the thing is to pass from the pair. So if you take A, you can pass to localization by P. So pass to localization by P. And meaning that you have multiplicative set A without P, and it is notice that it is also multiplicative set in B. Yeah? So when you're thinking about multiplicative sets, they preserve if you enlarge the ring. And geometrically, what we will see that A becomes local ring, so everything dies outside. So here you have you kill all the points that in the spectrum, and so this is spectrum of A, this is spectrum of B, and one can notice that localization. So if you have a function, yes, so on spectrum of A, then you can think of it as the function in spectrum of B with set of zeros corresponding to preimage of the set of zeros. And localization, it kills all the varieties that lie in the set of zeros of the functions on localization. So it is clear, more or less clear, that so you have the preimages here. Yeah? And only ideals in the, so if you think about geometric objects here that project here, yeah, so you can kill it by saying that you throw away the hypersurface with a set of zeros passing through this closed set. That means that you throw away the hypersurface that contains its preimage, and then you get rid of all of the stuff which sits outside. So this allows us to focus precisely on this formula, but from the commutative algebra, it is just what I was saying, it is just a half of the work, because so if you have beta that beta that intersects this set non-trivially, so beta beta, so let me put gamma, so that is ideal in B, that intersects A without B non-trivially. It is killed by localization. It becomes the whole ring, built by localization by S. So this implies that if you have beta that is not killed, it should have the property that this it is contained in the complement to this multiplicative set, so beta intersection with A is contained in P, but this of course implies, so since beta intersection with A is prime and not equal to 0, this implies that beta intersection with A is precisely P. So these are ideals lying over P. So precisely ideals beta 1, beta n, which we are interested in. So beta 1 and beta n. So spectrum after localization consists of so spectrum after localization, it is just consists of beta 1, beta n. Yeah, so beta k. So what about the values? Yeah, so the values of that p are in the formula. So trivially we have since you take p beta and you take this already this equality, the beta they map precisely in the corresponding beta after localization. So this is also equality.
So and what is the S set that we localize B by?
Complement to B.
Localize
In A. Complement to P in A.
Yes, and we localize by in B.
Yeah, I mean it is multiplicative set. So in order to localize it, you just have to have multiplicative set. So geometrically means that, so if you take multiplicative set downstairs, so this is collection of hypersurfaces.
Yes.
I mean, it could be finite to infinite. Yeah. So after localization downstairs, you throw also varieties that are contained in some hypersurface, yeah, or in this set. And upstairs, the set of hypersurfaces, you take preimage, yeah, and then you have again the union of hypersurfaces. However, it is smaller. I mean, you do not have these hypersurfaces are precisely come from preimages. Yeah, so there could be horizontal, yeah, so horizontal hypersurfaces, but not for finite morphism. Yeah?
Yes.
So that's why we have we get, this way we get rid of everything that is not mapping to P. And but the equality preserves, and yeah, also after localization, BS is still dedicant because being integral closed, it is satisfied. And moreover, you may think that you have already this decomposition, and after, we have to think about the distinctness because you have to think that this decomposition is unique. Since we have defined these numbers by, that you have taken some decomposition and put this number. But anyway, so beta S is dedicant still is still dedicant. So you use the same decomposition. The only small moment is about beta S. The FIs, which is B modular BI over A modular P. But after localization, notice that already in S is already invertible in A mod P. And if you think of localization, localization commutes with taking quotients. Yeah, so if you take just more generally, yeah, so if you take the exact sequence of modules, M1, M2, and M3. So when you localize, so this of course means that M3 is equal to M1 modulo M2, M2 modulo M1, but when you localize it, so localization of M3 is just localization of M2 modulo localization of M1. Yeah, so this is not, so this should be checked, but this is a basic property that I propose you, if you have not met of this, I propose you to do it as an exercise. We'll look in T. M. McDonald just at the beginning of taking, so for the chapter about localization. So this will imply that, so notice that S is already invertible in AP, so localization doesn't, over S doesn't do anything. Yeah? And for B modulo BI, since it contains it contains A modulo P, so and also in B mod BI. So the fields, so these objects are really preserved after. So for example, so they preserve under operation of localization. Yeah, so that this is just B modulo BI, yeah? And the same is for A. Yeah? So this means that if I preserve, so we can assume that A is a local ring. So A is the dedicant local ring. So I assume that A is a dedicant local ring. So this is principal ideal domain. And if you consider principal ideal domain, then any ring, notice that B, so it is, so we have proved, so since we have proved by trace, by using trace, that B sits inside A over D, A, N, and yeah, so B is the subset in L, that L is isomorphic to K to the power N as a vector space, here, so as K module. And so in this vector space we have chosen a basis for some B, so that we can put B inside this A module. So this means the following, so this means two things, yeah, so that first of all, since we have principal ideal domain now, so a module, a submodule of a free module for principal ideal domain, so let me have N, so A is a principal ideal domain. So this implies that N is free and of rank N is submodule. A submodule. Yeah, A, of course it will be B. Yeah? So I prefer to formulate the general propositions with different classes. Yeah. So N is free and N is isomorphic to A modulo K. And so for some K, but for K less or equal than N. Yeah, so you have a notion of rank. And actually it is the following, so you take, so how it is proved, yeah, so you take N, it is finitely generated, so you use Noetherian property, huh? So you take generators, and you write them down, so since you are working in a free module, you write them down as in terms of coordinates. So this gives you the matrix. So mainly this is a question of of writing down the matrix with coefficients in A. So these are generators of so these are coordinates in A. So this is more or less. So the problem reduces to the following. So you are writing down this matrix. You are allowed to do the following operations, like operations of changing coordinates in AN. This corresponds to changing operation with rows. And you are allowed to change generators. These are operation with columns, and in the end of the day you are by this kind of operations, like you are allowed to add just one row to the other, add one column to the other, or subtract, multiplied by the number from A. Yeah, so you are allowed to, like these operations. Well, of course you are allowed to change rows and columns, but you are not allowed to divide. Yeah. So after this, the ideal of so this proposition really tells you that you will have diagonal matrix for the generators, and you will have divisibility property that first will be less divisible than so actually the more or less if you want to recall the algorithm of doing it. So here the situation is quite simple. You have this uniformizer. So the elements are just start with so these are invertible elements times the power of p. So you take the element with least power of p, put it in the angle by changing rows and columns, put it here, and then you subtract it from here and from here, yeah, so to obtain 0. If the elements are not divisible by it, yeah, so you divide with remainder, and this means that after division you will get the element with lower divisible by lower power of p, and you repeat this procedure. So more or less this is the algorithm. Of course, one can just do it in a little bit general setting. So, but this, I mean, anyway, I'm not going to discuss this theorem. It is contained in the standard course of algebra in HSC, and so you have this divisors. So what I want to recall that di divides. So this is less divisible. So di divides di plus 1. Yeah. So they are these are increasing sequence of divisors. So notice that we have not only bound that B is a subset of an. Yeah, so from the beginning, so in the proof we also proved that B contains an, and this means that. So this implies that B is just isomorphic. So in our case, B is isomorphic to AN. However, I mean that is so the embedding, how it is embedded. So since you can divide, so these choices not canonical in any case because this is. Refers to the choice of basis. So I mean that it can happen that you can choose the basis, the initial basis by with the elements divided by something. So I mean this B still can be thought of a subset. So yeah. So let me now. Consider. You have the set which is isomorphic to AN, so this is B, and we want to apply the following. So we want to pass to B modular B P times B. Yeah. So from the viewpoint of notice that since B is isomorphic to B as A module, this is just A n modular PAN. So as A modules. So this is just A modular P and the power n. So notice that P is maximal, so this is a vector space. So just a vector space. So now we have to calculate its dimension in a different way by using our other data. So maybe it is a good point to make a break. Ну что, минут 10, да? Нічого, продовжуємо. Yeah, we noticed that our thing is really a vector space over the field. Yeah? So let us try to calculate it in a different way. So recalling that PB is now the product of BI's 1, etc. B and K. So notice that first of all, so BI POS coprime. Yeah, and the product is just the intersection. So this means that PB is just equal to intersection of BI and power I. So by Chinese theorem, remain the theorem. So here you have P mod beta P beta. Is isomorphic to what? To the product of B mod beta I. Yeah? So this is a product with the corresponding rings. However, notice that here you have clearly you may think of this as follows. So you have a ring that is a product of this ring. So dimension of the vector space of this vector space is equal to dimension of this vector space. Yeah? So but of course this notice that what we can do with beta EI. Yeah? So what we can do with this thing? Yeah. So here you have filtration. We have to consider this thing as of course, what is not clear here, so this is a product of the rings, and a posteriori, so this is a product of A modules, yeah? So, inside, so the vector space, it is not clear which structure of A modules it has, and what structure of the vector space, but we know that this vector space has decomposed. Yes, so we have a dimension of this B over beta I E over A modulo P, yeah, is equal to so the sum of dimensions over I is equal to n. Yeah? So we have to understand what are dimensions of this vector subspaces. But what data we have Fi here, or beta, so these are dimensions of B over beta over A mod P. So this means that we have to estimate the dimension of this thing, And this thing is now filtrated. The B itself is filtrated. So you take B. It is B, so here it has B square, etc. So beta E beta. And now we recall that, so we assume that B is local, so here we can, when we're thinking about even about this stuff, we can localize by beta. Yeah, so here, moreover, actually, this is already a local ring. Notice that this,
This one.
yeah, so already.
Portion. Yeah.
Already this quotient, yeah, is already a local ring. So already local ring for B. With maximal ideal beta, for beta modulo beta E beta, but I mean for the image. And the reason of this that if we take, so in beta, we have finite collection of, so this beta G is a finite collection of ideals, so only maximal ideals. And beta G is coprime to beta, so this implies that beta G is coprime to the power. So they are coprime because they are both maximal. Yeah, so, and we have already used that, of course. Yeah, so since beta J is coprime, so beta J is coprime to beta E beta. Yeah, and this implies that they are both coprime. So this means that. So if you factorize by beta, then the image of beta G will contain a unit. So this means that only ideal is beta, the corresponding ideal, this ideal. Yeah? So if you already this this means that in order to calculate, already when we're calculating the dimension, we can localize, calculating dimension over A mod P. And so we can localize the ring beta by now complement to beta G. Yeah, so and so complement to beta J is just in the local ring. It is actually already the set of units, so it does not do anything. So this is already a set of units, invertible elements. So B can be thought to be already local. And this implies that So we, I mean, we can just. Yeah, so we can, I mean, we already can localize beta, but this doesn't affect, so we can localize b by p without beta g, and this set, I mean, this is set of units in b modulo beta e beta. I mean, it's not the set of units of the whole ring B, but when you localize it's already the set of units, so localization doesn't do anything with this quotient. So this means localization does not change b modulo beta e beta. And yeah, so now you have, now b becomes local, so beta is just generated by b. And this, yeah, so beta e is also power. So you have natural isomorphism, so beta modulo beta. Yeah, so you can map b mod beta inside b in the power I modulo beta in the power I plus 1. Yeah, so we are mapping element b to, of course, pi times b. Yeah. Okay. So this map is yeah. So since p beta is generated by p, so this map is surjective. So and this is isomorphism surjective. So this map is isomorphism, and this implies that if you think of, yeah, so you may think, so we can calculate the dimension of this set, yeah, so that can be calculated. Yeah, so using the following fact that you have a vector space infiltration. So you can, so dimension of the vector space over K is just the sum of dimension of associated graded factors, so that Vi modulo Vi plus 1. So here this isomorphism means that a dimension over K of beta I modulo beta I plus 1. Yeah, so this is precisely dimension of beta over p over k. So also, so here you have some yeah, so here you have yeah, so I mean, if you do not want to put everything in the vector space, so to say that these things that we consider are the subsets in the vector space, you may think of more general thing that is length. Yeah, so that. So this length function, let me actually write it down. So, yeah, so length function is the following. So when you study modules, not vector space, so modules over local rings, yeah, so for example, the modules of the form that we can consider here, so like B over BE, yeah, so the modules of this form. Yeah, so here, yeah, so notice that here, just then you have the following, so you can introduce the, so if you have A is the ring M, and suppose that M, so dimension of A is equal to 1. So dimension of A is equal to 1. So you do not have any prime ideals, and this implies that if you want to consider so simple modules that do not contain the proper submodule, so these are so only simple modules. So that do not contain proper submodule. So they are of the form A modular Mi. Yeah. So otherwise, you can do the following. You can take any ideal of A. Yeah? So if that contains your given ideal. Yeah? So if your ideal is not maximum, you just take the larger ideal. And then you can do the following. So what is the length function? So you have M, and we consider filtration. So suppose so this precisely about the statement about the modules of finite length. Yeah? So we consider filtration. Where Mi modular Mi plus 1 are simple modules. I mean, you can do it more generally, for example, where but necessarily so the modules should be of the form A modular M, because you can also always take an element. Yeah, so I mean, why this this is description? Because if you have a module M, you always have a map about A into M. This is just making the element A into A times M. Yeah. So this implies that you will have inclusion of A modular annihilator of element of A inside the M. Yeah, so if you have, if M is simple, then this inclusion should be isomorphism. And if So if annihilate is not maximal, is not so M is simple, then this is isomorphism. And if annihilate is not maximal, then you take M that contains annihilate of M. And this means that you take a mod M mod annihilate, and this is proper submodule. So a submodule. So I mean, if you want to generalize this picture, yeah, so this means that for the set of simple modules, you have to take a modular Mi when these are maximal ideals. So this tells you something about the filtration. Yeah, that you should have. So if you have a module if you have a module that have a finite sequence of modules such that filtration are simple modules, you may say that the length of function is the maximal length of this filtration. Yes, so the length of M is the length of this filtration. This tells you that so that this function could be thought as that this is sum of length. Yes, so that the length of the module is sum of length of these factors. I mean, if you do not want to say that they are vector space, but a priori you know that they are vector space because they are sitting in the vector space. But it may happen that they are not vector space in the case if you are not in the case to which we have reduced. Yeah, so that's why sometimes people do not write down dimension but length function. And so that means that length of this module from the viewpoint of and then you pass from this what we have done so far, so that length of V modular beta E is just the sum of length x of beta E beta I modular beta I plus 1. Yeah, and these are isomorphic modules here, so this is just and if we want to speak about so the dimension of this thing over here, A mod B, is the sum of dimensions. And these factors are isomorphic as B modules. Yes, so this is just what? This is the number of factors times the dimension of, so since beta I modular beta I plus 1 is isomorphic to beta mod B. Yeah, so this means that it is E beta times dimension of beta mod beta over A mod F. A mod B, and this is just F, so you have A beta times F beta. So our vector space is the sum of factors. Each of them has this kind of dimension, so we obtain the formula that the dimension of n is just dimension of beta p beta over a mod b, and this is just the sum of p beta f beta. So we have this formula. And notice that it really tells you that, for example, when n is equal to 2, yeah? So this means that one of them should be equal. So what are the options? Yeah, so that
1 plus 1.
yeah, 1 plus 1, 2 plus this, 2 plus 0, and 0 plus 2. So precisely what we have seen in our extensions. So this formula gives us this formula gives us possibilities for quadratic extensions. Yeah, so let me pass to the following topic. So let me discuss something about the class group. It is a natural generalization and precisely so let me just say something about the class group. Yeah, so we consider the fractional ideals. So notice that fractional ideals form the group under multiplication. So that, yeah, actually we didn't discuss it yet, but this simple from both definitions. Yeah, so if you are allowed to multiply both of the ideals by the number that makes them usual ideals, the product of ideals is again ideal, and if you do not have to I mean, of course, these definitions are equivalent in case of when we are speaking about Noetherian rings, because we have derived that. So we had two definitions. One is that is fractional in K if it is finitely if I is a finitely generated module, generated a submodule, in K, or we can think that so there are or if there exists C such that, well, that we can consider in A, so such that I C times I sits inside A, yeah? So it becomes usual ideal. And here, of course, you can think of the numbers C1 times I plus C2 times J, which is ideal in A. Or you may think about, yeah, and of course, yeah, so in order to derive out of this, to derive first part, yeah, so you should have finitely generatedness of any ideal in Yeah, so this is equivalent to, so this is Noetherian property. So, so here arrow this uses Noetherian property. So, if you think about just finitely generated modules, so the product of finitely generated modules is the image of the tensor product, and we know how to generate it. So, just a second. That yeah, so so if I and J are finitely generated, then I times J is, so you can obtain that as an image. For example, I mean, even this is finitely generated. So this, yeah, so we can form the, and we can also find the inverse, yeah, for ideal. So you have this formal group, and then we want to understand the abstraction of the ideal to be a principle, yeah, so that abstraction to condition of factoriality, yeah, so that any ideal is principal. And this can be viewed as follows. So you can take ideal class group and factorize it by all principal ideals. Fractional ideals groups. So fractional ideals modular principal ideals. Principal fractional ideals. So this is called the class group of A. Yeah, so this, yeah, so this group is quite important. If it is trivial, then it is, so your ring is principal ideal domain, yeah? Because any ideal, you take it, you map it to the class group. If it is trivial, then of course it, so it is what you need. So,
why is PID? Can you?
This for trivial reasons. You because I mean, class group, you take fractional ideals, so meaning that it is zero in the class group means that it is principal. Principal, not prime. I mean, if the modular prime ideal, so this is already zero because any ideal is decomposable.
Oh, yeah, of course.
Yeah.
That's true.
I mean, this measures if, but what is interesting about this group that in our case, so the theorem that we are going to prove, so if A is a number, so is a ring of algebraic integers, algebraic integers, then this class group is finite. So which is non-trivial. I mean, this is completely non-trivial and non-evident fact.
What do you mean by algebraic integers? Integers or what?
Always, I mean, just integer numbers. So just A is integer extension of finite integer. So this is this actually tells you that in order to express any ideal, you need only finite number of generators, finite number of prime ideals, because I mean here you have finite collection of generators, so they are expressed into the finite collection of prime. So just so up to the principal ideal, you need only finite number of prime ideals to express something. And this also tells you that only finite number of prime, up to multiplication, so only notice that if you take prime ideal, you cannot multiply it, so it will be prime. So will be still prime. So this means that up to so only finite number ideals will be not principal. Finite number. Нет, это ничего не то. Это чушка. So so this is just forget. so let me prove. So let me do some additional remark. So that will be the main idea of the proof. So this will be norm of ideal. So norm of ideal. Yeah, so suppose you have so a ring extension. So integer extension of A, and A is integrally closed. Yeah, so where A is integrally closed. So in its field of fraction, Then I want to understand, just this assumption was in order to guarantee that the norm of B sits in A and trace of B sits in A. So this construct the following. So I want to construct the map between fractional ideals of A and fractional ideals of B. Yeah, so the fractional ideal A, how you map it to fractional ideals of B, just by two fractional ideals of B, by taking pre-image I times B. And we want to consider the operation that, so of course you can take intersection of the ideal, but I mean you can take the ideal and you can this thing and the inverse thing. You won't have the same ideal because either you won't have the ideal multiplied by something, and the reason is, so what I mean that I want to have some, and I want to have some kind of maps that are just so that will allow to map, so to take ideal and to take its pre-image, and I want to identify the map, so I want to have a map in this direction, not only ideal of and with the corresponding ring A, but I want to measure the multiplicities of the fiber somehow. I want to keep track on them. And in order to do it, we introduce moreover, you have this, so here, this map actually is some kind of push forward. And also we have why I was saying, defined on the set of elements. And if you have the set of elements, then the elements of B, then you have corresponding ideals generated by them. Yeah? So principal ideals. So it is natural to introduce norm of the ideal B should be just ideal of the norm. Yeah? And so you take the norm of element and you take this product. So the norm map that should map in this direction should take into account some kind of data.
And what is A?
What? Norm of B. Yeah. Sorry. Yeah. So. This, actually, so here it is, if you want to say that this is norm, it is, it should be convenient to call it by different letters before you prove that they are equal, yeah? So this means that the operation of norm on the ideal, it is just the operation of taking. So here I introduce so taking norm of the element. Yeah. So this is element, and this is ideal. It is natural requirement. So we have to. Just define the norm in order to fit. And and then to check that it is well defined. Yeah? So we do it as follows. So we introduce the norm of prime ideals and norm of beta, and this is just so beta lie over p. So beta prime to be prime ideal of B. And you reduce the norm by putting not only p, but p in the degree of inertia index. Notice that here it depends from factor to factor.
So, and we want to define norm function as a map from fractional ideals on B to map fractional ideals on.
Yeah, so this is a map from fractional ideals. Yeah, so it is defined by I. Yeah, so we'll I just recalled the notation. So let me. Gothic I. Yeah, so let us put it. Yeah, so this is I of B divided by just mapped to I of A by multiplicativity. Yeah? So multiplicativity. So extend. So the idea is that you can take you can take the following. So you can take. So you can start with P. Yeah. Yeah, so just yeah, and that map, that map that is just is defined here. It is natural. Natural to define like I star like this. Yeah, so I star of B. I mean this one. Yeah. So this is actually pre-image. Yeah. So this now you can take you start with P and take a norm. So take I star of P. So remark. I mean the remark why we're bothering about this definition and why we have put f beta here. Yeah. So remark everything is defined in order to have the equality, so that the I star of p apply the norm to it. It is just p to the power n. So multiplication by the degree. Yeah? So this is simply by, of course, it is, yes, so this simply follows from our formula because I star of p it is just you have to take p beta you have to decompose it into the product of beta E1, beta En, beta K. And if you apply norm map, then it is just you to each beta you take p in the corresponding power, which is so p and the fi index. It is multiplicative by our definition. And this is just p to the power n, since we have the formula here beta f beta is equal to n. So we have defined the formula like this, and the question how this norm is related with so when we have the rings over integers, and this is quite interesting. Yeah, so this just a second. So this here you have. Yeah. So the question is how this formula is related with the integers. So notice that over z, we have the following property to the ideal inside z. Yeah? So we can associate number which is ideal itself. Yeah. So I mean any ideal is principal. So we can associate this number n, and n is just the set of elements in the quotient. So n is the set of elements of z modulo n. Yeah? So this is the number of elements of A modulo I. Yeah? So more generally, you can of course do the following. So you can just introduce norm on the ideals. So you can introduce this norm on the ideals. Of algebraic integers. So norm on ideals of algebraic integers. By saying that you just take this A modulo I. So I mean you have A, you have ideal I, and you take the quotient. Yeah? So A, and calculate the number of elements there.
But that works only for ideals, not for fractional ideals.
Yes, this works for only for ideals. Yeah, so this you calculate. Because fractional ideals is not contained in A, but then you have a trick how to extend it. Yeah, so that you multiply by C, and C is a number.
Yeah, okay.
I mean, so it is sufficient to multiply by the number not in A, but then it is sufficient to multiply by M. Since A is the set of algebraic numbers, and yes, so let me comment on this. I mean, but later, yes. So that So the norm of the ideals is just the number of elements in A modulo I. Yeah, so that so the only thing here, so you have to notice that this is a finite group. So this is a finite group actually for yeah, so yeah, so this is first of all you can just yeah, so this is a finite group and a finite abelian group. Yeah, so what you know that A is a finite module over Z. Yeah, so A is a finitely generated module over Z. And what is important here, yes, so that if I is ideal, so A is finitely generated module over Z, and we have to understand that so this group at least is finitely generated. It has few components corresponding to Z and finite group. But notice that if just from the viewpoint of B, yes, so that you have a ring B, it contains I. Yes, so I is generated at least by an element. I mean, so there is at least one non-trivial element here. So I contains A times B. Yeah, so for some, I mean, generally, I want to formulate, yeah, so that suppose just to comment on our theorem on modules. So we had L over K. Here you had the extension A, and here you have integer extension B. Yeah? So you have just in this setting, we have bounded B by AN and by 1 over D AN, where N is the degree of the field extension. And also you have, if I is ideal in B, yeah, so we can bound the ideal by, so on one hand the ideal is contained in B, on the other hand the ideal is sufficiently big because you can take an element and multiply by it. So you can take an element A and multiply it by B. Moreover, I mean, so as B module, moreover actually you can take it, so since we have proved the intersection with just the I intersection with A is non-trivial for non-zero ideal, yeah, it's not zero if I is not equal to 0. So this element so we didn't use primes actually. So we can take, we even can assume that A belongs to A. Yeah, because it is just the element taken from B. And this this really means, from our point of view, that I is bounded between 1 over d an, and it contains a n times a. So this is the group of this it differs from an by multiplication by b. Yeah, so here I just taken the element from b, or more generally you can take it from the intersection of I and a, and this is not 0 because we have proved this. Yeah. So you have this kind of inclusion, and you have this kind of inclusion between the rings. So this means that if you multiply b by some a, it will be inside I. So this means that if you factorize b mod I, can be obtained as a quotient by b mod AB, and this is finite group. So this is finite abelian group. So this means that B mod I is finite abelian. Yeah, for finite, I mean finitely generated module, which is I mean from the, it's not good to say about this. So finitely generated module annihilated by so this is finitely generated module. So, yeah, so this I mean that this is a subset of an modular AB, an, and this is just, yeah, maybe this is a subset of and I mean if you allow to multiply by d, yeah, to divide by d. So this is just finitely generated module over A annihilated by A inside A, and for Z this means that if A is equal to Z, so when A is equal to Z, so this means that B mod I is finite abelian group. It's finite abelian group. So the claim is that yeah. So also you can so the claim that our norm map sits in the polar setting. So you have I of so associating the number of elements is just the following. So it is taking I of A, taking to be mapping to the fractional ideals of Z. And then mapping, taking the number of elements in Z. Yeah, so just taking the number of elements. So this maps everything to Z. And so you can do it instantly by taking I and taking the number of elements in A mod I. So wait. That our norm map is sits factors of this thing. So that's why. So that is. Of course. So as for me, I would be satisfied if I just take this thing, but I need this composition in order to settle it. And so the claim, which is claim is which is not so trivial, that this map is consistent with usual norm map. Yeah. So I mean that was motivation, and now we see it as the claim. So that norm map of the element A is just this. Yeah. So it is integer. Yeah. So notice. Maybe. So you can. So let me put the claim about this norm without taking the number of elements and the width. So if you have the map from IB into I of A, yeah, so you can take the norm map between these guys, and you can take you can take a norm of ideal corresponding to B. So this is a principal ideal. And you may take the norm of element and consider the ideal. So that will be the same. And then just after, so since if you are thinking about integer elements, then just this, if you take ideal, the norm will tautologically correspond to the number of elements. So this picture is consistent with this picture as well. Yeah. So yeah, so maybe it is, I shall do some comments. Yeah, so also let me say that, maybe I will just say some final remarks about norms, and then I will finish by saying that, so next time we shall discuss the theorem of finiteness of the class. So also we can introduce the following object. So here you have, suppose, we can introduce K groups. So K group of A is just the set of modules, set of A modules. And equivalence relation, so we say that M1 is if you have exact sequence, M2 and M3. Yeah, so we see that in our group, so it is just a free group generated, those generators correspond to the modules themselves, and up to relation that if you have exact sequence, we are saying that M2 is equal to M1 plus M3. Yeah? So if you have the group of B modules, so B module, so if A is contained inside B, so a B module M can become just, you have, so it can be considered as A module, so can be considered as a module. Yeah, so this operation is called restriction. Yeah, so that we can say that restriction of M from A into B. Yeah. So then also you can map it in the inverse way. So if you have A module, so there is natural operation that makes it B module, so which is what? Tensor product with B over A. And here we have we can introduce the following. So we can introduce also the norm maps. So suppose you have a module with filtration. Module with filtration. So here you have filtration so such that Mi modular Mi plus 1 are simple A modules. Yeah, so meaning that for Dedekind ring means that they look like, so A is Dedekind. This means that you have A mod Mi where Mi are maximal. Yeah? Maximal and non-zero, yeah? Because A is not simple itself. So I mean prime and non-zero. Yeah? So
zero is not maximal.
No doubt. This so if you have, we say that the module is of finite length. And on K group, notice that you can generate K group by the modules of finite length. So this is filtration. So this is called module, also module of finite length, as before. Speaking about of length, we do not grade it by the type of the factors. However, one can do it, yeah, because you have probably have proved in the course of basic algebra that if you have factors of them, so if you have a sequence of modules where the factors are simple, so that this sequence, this filtration is unique up to the permutation. Yeah? So the number of factors of, if it is finite, yeah? So the number of factors of different type is fixed. So Then what we have done so far, it is just the map from K groups. From K group of A, we can map it to ideal class group. Via the following, so notice that so just the A mod the MI, you can map it to the corresponding ideal MI. So this now just the motivation for introducing norm that it fits in the corresponding diagram of groups. Yeah, so that simply, yeah, so this is called chi of A, like early characteristic. So here you have the following diagram. So we define chi of A mi by putting mi, and by additivity, so we extended it by multiplicative on the factors of filtration. Yeah, so on the module with filtration. And so you have here you have chi of B to I of B. Yeah, and here you have natural restriction map. Yeah. And here you have norm map that we have introduced on the set of ideals. So that's why this is important. And yeah, so if yeah, so if A is let A be a ring of let be A be a principal ideal domain of proposition. Then for n xi psi b, so this will mean that the norm of psi is equal to applying chi this so restriction of b modulo xi b. So the element of K group and applying I. Yeah, so notice. So this is
C from where? From
psi from B. Yeah. So so this will be we shall discuss later, and we shall also discuss how to how to use it and to reduce
yeah, and how
to check this equalities.
how I connected to C.
Извините, да, конечно. Ну.
Ага.
Очевидно, да, очевидно. Ну, просто как бы, да, можно думать об этом как о модуле над B. И, ну, как раз вот это вот ограничение, это до того, как мы берем фактор группы, да, ну, то есть как бы So notice that this is generalization of what we were discussing, just because if you put Z here instead of I mean, instead of k of z. This will be just the n, and so the ideals here. And this map will be will say that you just I mean, this will be precisely the calculation of the number of elements, because let me say it explicitly. So here you take z, here you take I of z. Yeah. So here you have norm map I of A, and here you have k of A. Yeah, and if you think of this equality, yeah, so that we just how we would obtain. So we have taken I here ideal. Yeah, for example, we have taking a modulo I, and we were saying that we calculate the number of elements. Yeah? But this means that we consider it as a abelian group. So this means that abelian group. So means that we can consider it as Z module. And this really corresponds to restriction of this side. And here you have taken the norm. So here it's chi of A, and here is the norm map, and here is a calculation as the number of elements in this group. Yeah. So this is a map to Z. It is calculating the number of elements. So that's why I mean, this is a part of this picture. So this, I mean, this is a small refinement of what is going on here, and this, yeah. So this we will explain. So this refers to how the so of course we shall use this, that it is a principal ideal of the domain as by the fact that n is a module of the free module is free. Yes, so that you can pick the basis. So so next time I shall finish this discussion, and we shall apply this norm map to the ideals, and we can prove the class finiteness of class, which is quite important theorems. So this is one of the basic theorems for integer numbers, and there are also the theorem that maybe it is even deeper. So this will be the theorem on Dirichlet theorem on units. So that is description of invertible elements in algebraic number fields. And but the very beginning of this theory is finiteness of the class group. So we shall see the main ideas that allow to guarantee finiteness, and then we can extend it to the setting of Dirichlet theorem from the set of fields.